Welcome. My name's Connor Leahy, and I'd like to invite you to explore our knit-lined paraxylene plant. We are Team 12, the Donovan McNabb Faddens, and I'm joined with Benjamin Hitch, Ahmed Akabasi, Ahmed Salah, Kaylee Lazaroff, and Lucas Dubiak. We would like to welcome you to our knit-lined chemical plant, and we'd like you to get comfortable at our facility. Our team was assigned with a toluene flow rate of 45,000 pounds per hour. Within this presentation, we'll go over the plant and product general information, the plant economics, and future recommendations for our plant. The main chemical products at our plant include benzene and paraxylene, as they are essential industrial precursors. Benzene is usually a byproduct of oil refineries and chemical plants. The process varies for its production. Benzene is used mainly as an intermediate to make other chemicals. About 80% of benzene is consumed in the production of three chemicals: ethylbenzene, cumene, and cyclohexane. Smaller amounts of benzene are used to make some types of rubbers, lubricants, dyes, detergents, drugs, explosives, as well as pesticides. Paraxylene is a precursor for many other industrial chemicals. The most important chemicals include terephthalic acid, purified terephthalic acid, and dimethyl terephthalate. These three chemicals are used in the manufacture of an important polymer known as PET. PET is very common plastic that is widely used in the manufacturing of plastic bottles for beverages. Our plant will be located in Houston, Texas, and will produce 238 million pounds of combined 99.9% paraxylene and 99.9% benzene. The plant would be constructed at Knit-Line's existing plant in Texas along the Gulf Coast. Houston, Texas is located on the ship channel, and this production facility has access to many pipelines to supply materials. The existing plant already has much of the basic infrastructure available, but some upgrades and modifications would be required to handle the extra capacity. The plant is to have a life expectancy of 15 years with a target rate of return of 15%. All estimates made were based around an operating time of 8,400 hours per year. Before we move into the financial and technical analysis of our plant, we would first and foremost like to announce that our plant's products meet all safety and environmental specifications. Within our safety protocols, release models will be constructed for the chemical products. Parameters for safety and exposure will be acquired from OSHA, the Occupational Safety and Health Administration standards. These regulations will also be examined by a legal team to ensure plant practices are in accordance with the law. Since benzene is a carcinogen, proper equipment is required where respiratory protection is key. Benzene is also flammable, so it is very essential that proper personal protective equipment is worn. Exposure to xylene would be avoided by correct sealing in storage tanks, and we will place them outside the facility to allow ventilation.
Hi, my name is Ahmed Saleh, and I will be talking about the products of the plant as well as the process as a whole and the reactor. The main products of this plant, which are benzene and p-xylene, must be at least 99.9% pure in order to meet sellable specifications. The mixed xylenes can also be sold if they also meet a 99.9% purity. We designed our plant to produce 13,583 pounds per hour of paraxylene with a purity of 99.94% and 14,760 pounds per hour of benzene with a purity of 99.92%. In this plant, approximately 5,200 pounds per hour of mixed xylenes were produced as a byproduct, and they will be sold as the purity meets 99.97%. Our plant is designed for 45,000 pounds per hour of toluene as fresh feed, as well as 310 pounds per hour of hydrogen. The toluene is pumped to a pressure of 380 psi and allowed to boil in a heat exchanger. The two are then heated to a temperature of 750 and are sent to the reactor. The effluent of the reactor is then cooled down and sent to the vapor-liquid separator, where hydrogen and methane are separated as vapors and are recycled back into the reactor. The liquids are sent through a series of distillation columns to separate toluene and benzene, where benzene is separated as a product stream and toluene is sent back to the reactor as a recycle. Paraxylene is then separated from the mixed xylenes in the Parex adsorption unit, and the mixed xylenes are then separated from TMB in the third distillation column and sold as a product stream. The main reaction that is occurring in this reactor is the toluene disproportionation reaction, where toluene is converted to p-xylene and benzene. P-xylene can then go through isomerization and forms the other two xylene isomers. After the reaction has occurred, the hydrogen and methane from the vapor-liquid separator are sent through a hydrogen purification unit and then compressed back to 380 psi and then sent back to the reactor as the recycle stream. The liquids from the vapor-liquid separator are sent to the distillation columns.
Hi, my name is Lucas Dubiak, and I will be talking about the purification units in our process. The stream leaving the vapor-liquid separator enters the first distillation column, where benzene, which has the lowest boiling point, is separated from the mixture to a purity of 99.9%. The bottoms are sent to the second distillation column. The distillation column is 94.6 feet high, with a diameter of 7.5 feet. There are 37 trays, with the feed tray above tray 15, and the reflux ratio is 6. The bottom stream of the first distillation column enters the second distillation column, where toluene is separated from the mixture. Part of the toluene is recycled back to the reactor, and the remaining is sent to a storage tank. The bottoms is then pumped to the Parex unit. The second distillation column is 93.5 feet high, with a diameter of 10.9 feet. There are 32 trays, with the feed tray above tray 20. There is also a reflux ratio of 9. The Parex unit is fed by the bottoms of the second distillation column and goes through a pump to pressurize the feed to 87 psi. The unit separates p-xylene at 99.9% purity from TMB, ortho, and metaxylene. The Parex uses solid adsorption to separate p-xylene from the mixed xylenes. The p-xylene is sent to a storage tank, and the bottoms is then sent to the third distillation column. The bottoms of the Parex unit is sent to the third distillation column, where mixed xylenes are separated from TMB. The mixed xylenes are sent to a storage tank and can be sold since they are at a purity of 99.9%. The TMB is then sent to a flare. The distillation column is 63.5 feet high with a diameter of 3 feet. There are 18 trays with the feed above tray 10 and a reflux ratio of 5.
Hello, my name is Ahmed Al-Kubaisi, and I will be talking about the economic evaluation of the project. Mainly, I'll discuss where the revenue and cost lay. First, let's take a look on the graph on the right. We see that this is the sales revenue over time. We see a big jump in the year 2022, as that is the base year after the plant is done. The revenue jumps in the first 4 years and then slows down significantly. On the left, we see the pie chart showing the percentages of revenue based on the products made by the plant. We see benzene having 40%, being the second largest, and p-xylene, the main product, being 50% almost of the revenue. Following that, we have the mixed xylenes at 12%. Benzene has a really large percentage because of how much is made. The economic evaluation is possibly the most important part of the plant. What is the point of having a process plant that does not generate any profits for the company? I wish it were that way, that we're making products for charity, but that's not the case. First, let's take a look on the capital costs and where they lie. The equipment costs and area for the plant due to piping and other equipment were the main players. These values were obtained by first drawing the area of the plant and putting the safety features in it, and then specifying these equipment in Icarus and getting the costs. Following that, we have adding the operating costs for the plant. These were calculated as a function of the capital cost and also found in the Icarus file. Then we move on to the fixed costs, which were mainly the heating, the electricity, the water supply, and worker expenses in general. Obviously, after calculating all these costs, they were put in an Excel file and then analyzed to see which parts could be optimized and how revenue compared with the cost of the plant. Here we see on this slide two pie charts, with the main pie chart being on the left, showing total cost. toluene is the primary raw material that contributes to the cost, and the raw material in fact contributes the most to the total costs. Seeing the numbers cents per pound of product, the total ongoing cost of this plant is 53.7 cents per pound of product. The majority is raw materials at 81%, showing 43.5 cents per pound. The other 19% is attributed to utilities, labor, SG&A, and taxes. We can conclude easily from these charts that raw materials have the most impact on total ongoing costs. The process in general required heating at high temperatures that were usually between high pressure steam and medium pressure steam. Thus we see that the high pressure steam is more than half of what we pay for utilities, being 60% almost. As operating temperatures were usually high, we had to use cooling water to cool the compressors, provide a cool benzene stream for the product, and cool the condensers, so that a small percentage is seen at 0.22 cents per pound of product. The rest of these costs were used for fired heaters as for natural gas, power for the pumps, and low and medium pressure steams to provide high enough temperatures for heat exchangers to not cause such a high temperature gap and to not cause any temperature crosses.
Hi, my name is Ben Hitch. I'm going to continue walking you through some of the expense breakdowns. Here's a breakdown of the fixed costs that are associated with the plant. Labor costs account for 0.86 cents per pound of product. This figure is estimated off of 6 operators working 4 shifts. Overhead costs are 1.29 cents per pound of product and are calculated by multiplying the labor cost by 1.5. Repair and maintenance costs, property tax, and insurance are estimated by multiplying the capital expenses by 1.5, 2.5, and 0.5% respectively. Finally, the Parex unit has specific licensing fees and operating costs that account for almost a quarter of the fixed costs. Next is a breakdown of the equipment costs required to construct the plant. As you can see in orange, the Parex unit accounts for the majority of the equipment costs, with a total contractor cost of $38.8 million. Distillation columns in teal also account for a large portion of the equipment costs and are estimated to be $10.2 million. The hydrogen purification unit is in dark blue and costs $7.1 million. Our plant was designed to avoid using compressors, since the single one in our plant costs over $3 million. Other equipment within the IBL includes the reactor, a vapor liquid separator, heat exchangers, pumps, and a tank. This slide shows a plot that summarizes the plant's cash flow model. The x-axis shows the year, with the plant construction to start in 2020 and end by 2022. The next 15 years are the expected lifespan of the plant. The bar graph shows the after-tax cash flow for each year in millions of dollars, and the line graph shows the cumulative cash flow. Despite the plant's capability to produce a small annual profit, the overwhelming capital costs prevent this project from being a viable investment for Nitlion Chemicals. Capital costs are expected to be $127 million, with a large majority of the equipment costs coming from the Parex unit, as mentioned before. The team estimates that with a toluene flow rate of 45,000 pounds per hour, the return on this project would be about 21 years, well past the life expectancy of this plant. At the end of the 15 years, the plant would still be $35 million in debt. Here's a quick summary of the economic estimates for the plant, which again are based around an assumed annual operating time of 8,400 hours. As mentioned before, the plant has a capacity of 238 million pounds of benzene and paraxylene per year. We've estimated that the capital costs are going to be $127 million, and ongoing costs are going to be about 46 cents per pound of product. The cumulative cash flow at the end of the 15 years will be $35 million in debt, all of which gives an after-tax rate return of negative 3%. The team's target rate of return is 15%, and anything below this gave us an indication that the project is not a viable investment.
Hi, my name is Kaylee Lazaroff, and I will be discussing the PDRI and alternate designs to the plant. For the scope of this plant design, the team will only be focusing on front-end planning. which includes feasibility, concept, and detailed scope. Throughout these 3 steps, the PDRI is the most applicable in the determination of what is done, what needs to be altered, and the measurement of certain risks present in the design process. With a PDRI 2I score of 311, the detailed scope of the project does not define information about future expansion considerations or dismantling and demolition requirements. These 2 categories would need to be further explored during the construction process. The blueprints of the plant will also need to include possible areas where further expansions may be considered and possibly a plot of land where other buildings may be constructed. Realizing that our plant will not make money in the 15-year lifespan, we designed 2 alternative designs. The first one being that we would modify the hydrogen recycle unit. An alternate to recycling hydrogen would be to remove the equipment involved, such as the hydrogen purification unit in the compressor, and instead just increase the flow rate of hydrogen from the feed. The hydrogen out of the reactor can then be used in another section of the plant, such as being burned to use as a heat source for certain streams in the process, instead of using hot oil. Another alternative would be to purify TMB. Our base case model does not have the means of producing trimethylbenzene pure enough to be sold, where the majority of TMB can be found in the purge stream that comes from the bottom of the 3rd distillation column, which is roughly 70% mass. TMB at 99.9% purity can be sold for 32 cents per pound, which is about the same value as mixed xylenes. To separate this TMB, an additional distillation column, heat exchanger, and pump would be necessary. Overall, this alternate process seems to be a proper consideration and should be implemented if there is additional time and resources. If there is a demand of low flow of TMB and the amount of TMB produced can be sold for the price listed above, then this section will be profitable since it will generate an additional $22.14 million over the entire life of the plant. With the parameters given, our plant will not be making money in the life cycle of this plant, which is 15 years. Although under the right circumstances, the plant could be built if there was a higher flow rate of toluene feed, a larger raw material margin, a longer span of the plant, in which we estimate about 21 years to begin making money, and an increase of the price of the product sold. In addition, the Knit-Lion Chemicals Company will need to develop a catalyst that increases the conversion of toluene by decreasing the activation energy. With these plausible recommendations, the plant may be built under these circumstances. Finally, our team would like to thank our mentors Ryan and Joe, as well as Professor McFadden and Dr. Arend, for the help and support of the project. Thank you for listening.